Hey guys, so I wanted to give an introduction to Newton's third law in this video, which seems simple but is quite tricky, and there's many misconceptions that are pretty common about Newton's third law. So I want to introduce Newton's third law, explain some of the tricky parts about it, and then do a problem solving example where you would need to use Newton's third law to solve it. So what is Newton's third law? So there's many ways to state what Newton's third law is. The most common one that you'll find if you Google it or if you listen to people talk about it is they'll say every action has an equal and opposite reaction, which is very non-specific and not really in line with the way we use terminology now. A slightly better way to say it is every force has an equal and opposite force. So that gets closer because it replaces action with force, and forces are what we're talking about here. But I want to break Newton's third law down a little bit into a couple of different parts to explain them and to talk through some of the tricky parts of each part. So the first basic idea of Newton's third law is that forces come in pairs. Forces come in pairs. So that is, if I push on you, you necessarily push on me. If I push on the wall pushes on me. If I stand on the floor and push into the floor pushes back on me. If I experience a force of gravity, then something else is experiencing a force of gravity from me too. So forces come in pairs. It's not always obvious which forces are paired if you're looking at a free body diagram or a problem, because the pairs aren't always represented in the same diagram. So we're going to come back to that idea. But for now, I'm going to make a note. It's not always obvious which forces are paired. And that can lead to some conceptual trickiness and some sticky points in problem solving. Okay, so forces come in pairs. That's not all of Newton's third law, because Newton's third law also says that each force in a pair has the same magnitude but opposite direction. So let me write that down and then explain it. So each force in a pair has equal magnitude but opposite direction. So that is, forces are vectors. And what this means vector-wise is if I push on the wall and that force points a certain direction, then the wall pushes on me in the opposite direction with the same strength. So this is the equal and opposite part of Newton's third law, that the force that I apply on something is equal in magnitude to the force that it applies on me back, but opposite in direction. And we'll come back to this. When we do an example, I'll show you how to apply that idea. And the last part, which isn't stated in the typical statement of Newton's third law, but is really important to keep in mind, is that each force in a pair acts on a different object. It's really important to keep this in mind. If you think about what the second part of this said, so there's three parts here. Forces come in pairs. It's not always obvious which forces are paired, but then each force in a pair has equal magnitude but opposite direction. If you think about that, you might be compelled to say that, well, if every force has an equal and opposite paired force, then how can anything in the universe accelerate, right? If I push on something, but then there's an equal and opposite push back, then the total force has to be zero, because if I take a force and then add an opposite force to it, then I get nothing. So the net force is zero. And that's kind of true. So if you consider a system, everything within that system, like if you characterize the system as just one black box, then interactions like pushes and pulls inside that system cannot move the black box. But if you consider individual parts of what's inside that black box, if I push on the wall, I'm feeling a force from the wall, but the wall is feeling a force from me. So we don't always represent Newton third law paired forces on the same object in the same diagram. So I can have individual things accelerating due to forces. If you consider a system of more than one object though, any forces between them are going to cancel out. That's probably sounds a little bit crazy and hard to understand, but I hope to also show how you can apply this idea in a free body diagram. So I want to show you an example of how you can think about and apply Newton's third law in problem solving. So here's an example. I'm pushing, there's 2 blocks being pushed on flat ground. So push 2 blocks, or 2 boxes, I should say. And I only push on one of the boxes. So let me draw the boxes. So I'm gonna scroll down a little bit. So there's a box here. This is box A because it has apples in it. And then there's another box B, it's a bigger box. And B, it's box B because it has bobcats in it, obviously. Okay, oops. Okay, and here's the floor. Okay, so what I'm doing is I'm pushing the box of apples. I'm applying some force on the box of apples. And the goal here would be to analyze what's happening in the system. I'm just pushing on the apples. So I'm pushing this whole system to the right. So I'm pushing on the apples, the box of apples, but then the box of apples is pushing on the box of bobcats. And so everything begins to accelerate. We're gonna ignore friction here. So let's leave out friction, no friction for now, which will make things easier, but won't decrease our ability to think about Newton's third law in this context. So we're going to do 4 things here. The first thing we're going to do is we're going to draw free body diagrams for both of the boxes. So first, draw free body diagrams. Okay, for both boxes. Then the second thing we're going to do is identify the force pairs here. So identify Newton's third law pairs. And then we're going to actually quantify some of this stuff. So we're going to give the force a value. So if force is 20 newtons, and I give masses to each of the boxes. So the apples weigh or have a mass of 5 kilograms, and the bobcats have a mass of 20 kilograms. Then we'll find the acceleration of the boxes. Okay, and then the fourth part, last one, how much force is exchanged between the boxes? Okay, 4 parts, a couple of more conceptual ones and then a couple of more quantitative ones. I'm going to do the solutions in a different color because I can. I'm going to do it in red. So for 1, let's draw free body diagrams. I'm going to take each of them in isolation just to make it really clear which forces are acting on which box. So if I draw box A, the apple box, apples. There are several forces acting on this box that I can represent on a free body diagram. So first is the force that's being applied, F. So that's the force that I'm pushing on the box with. That's 1. There's also a force of gravity here. So force of gravity goes down. mg, I'll write it as mass times gravitational constant, mg. There's also a normal force from the ground. I'll call that n, normal force up. And then also, if I'm pushing on A, and box A is then running into box B, there's got to be a force that B is applying on A. B is pushing into A as A pushes into B. So that means that there's a force, and I'll call this force of B on A that goes to the left. So that's going to reduce the overall acceleration of the system, if that makes sense. If I were just pushing on block A with this force F, then or box A, excuse me, then the box would accelerate at some rate. But because box B is there, it won't accelerate as fast. There's less net force on this box. We don't know the magnitude of any of these forces necessarily. We haven't put numbers on this, and for this part, it's not necessary to put numbers on this. But we know for sure that F has to be bigger than FBA if this whole system is going to move. And if there's no friction, it should move. It might move really slowly, but it'll move. So F should be bigger than FBA. We can write that for sure as something we know. And we also know that if this thing is moving just horizontally, that the normal force here should be equal to mg. Okay, that's the first free body diagram. Second free body diagram. Okay, so let's draw the second box. So that's the box of bobcats. So here's the second box, bobcats. All right, so there's some of the same forces on this box as on the Apple box. But so let's draw those first. So there's gravity here too. And I guess on the Apple box, I should denote the mass here as m sub a for the apples, capital A. And there's the same force of gravity here on the bobcat box. So there's mb times g down. Okay, and there's a normal force up. And now to be totally distinct here, let me call these different forces. So I'll call this the normal force on B and the normal force on A up here on top, just to be clear. And it should be the same as in the first case. We should have that the normal force on B is equal to the weight of B2 because we're only moving on this horizontal surface. But why is the bobcat box moving? If it is moving, what forces act on it to cause it to accelerate? Well, we are pushing on the Apple box, but we're not pushing on the bobcat box. So our force is not directly applied on the bobcat box. It seems like that is the thing that's causing the bobcat box to move, and kind of it is, but the direct thing that's causing the bobcats to move is the push from the box of apples. So the Apple box is in contact with the bobcat box. Therefore, the Apple box is applying a force on the bobcat box. So there's a force from A to B here, FAB. And that's it. That's the only force that's pushing the bobcat box forward. And you'll notice that I've called that force FAB, the force of A on B. And on the previous diagram, I called the force here the force of B on A. That was the force that the bobcat box pushes back on the Apple box with. So those are paired forces, FBA and FAB. They're equal in magnitude, but opposite in direction. So we'll come back to that. But this is a complete free body diagram for this model of what's happening, where we've ignored friction and we've ignored a lot of other complicating forces. We got our force is pushing the Apple box is pushing the bobcat box. There's a force of gravity and the force of the ground that are offsetting in the vertical direction, and all the real action's happening in the horizontal direction. Okay, so let's try to do the second part of that. So that was the first part, draw free body diagrams for both boxes. The second part is identify the Newton third law pairs. So I'll make a little box for this. So identifying force pairs. All right, so we just talked about one. We talked about FAB and FBA. Those are forces that are paired together through Newton's third law. The apple box pushes on the bobcat box, that's force AB. Therefore, the bobcat box pushes on the apple box, that's FBA. So that means FAB and FBA have the same magnitude in opposite directions. And you can see that the opposite directions, at least, indicated on the diagrams. FBA points left on the apple box, and FAB points right on the bobcat box. And at the top of this video, I had 3 bullet points for Newton's third law. The third one is that paired forces always act on different objects, and you can see that here. So these forces, which are paired together, are equal and opposite. One of them acts on the apple box, and one of them acts on the bobcat box. So there's none of this conceptual confusion about how can anything accelerate if they're the equal and opposite forces, because they act on different things. So if you just take the bobcat box, for instance, FAB is definitely accelerating the bobcat box. It's the only force acting on the bobcat box. So just to point that out here, that's how that works. Other force pairs here. The only other force, there's the force of our push, there's the normal forces, and there's gravitational forces. Let's handle the normal forces next. So I'll say NA, so that's the normal force on box A. That force is not actually paired with any force on these diagrams. The normal force is the force of the ground on the apple box. Therefore, there's a force of the apple box on the ground right underneath the apple box. But because we haven't drawn the ground, we haven't drawn the forces on the ground, the equal and opposite force to NA is not on this diagram. And force from A on ground. So that's what the paired force would be, but it's not shown on the diagram. It's tempting to say that the force of gravity on the apple box is the paired force with NA, but that is not correct. The normal force here has nothing to do with the gravitational force. The gravitational force would exist whether or not the apple box was in contact with the ground. So you can see that they can't be paired, because if I just lift the apple box off the ground, suddenly there's no normal force with the ground at all, but there is gravitational force. And Newton's third law says that paired forces always have to be equal and opposite to each other. Even though NA is equal to the force of gravity on A here, that is it's not a coincidence exactly, but it is true, not because of Newton's third law, just because of the physics of what's happening here. So that's a really important point. But then what is the paired force to the force of gravity on block A? Well, there's a force of attraction that the box of apples has with the Earth itself. So that's a force of gravity that the apple box exerts on the Earth. And that force of gravity will always point towards the center of the Earth. So that there's a gravitational force with the rest of the Earth that the Earth experiences, gravitational force that Earth feels due to box A. That's so like even if I lift the box up, there's still this attractive force that's gravitational. That doesn't require any contact between the Earth and the box of apples. It just requires that the box of apples has mass and that the Earth has mass. That force, again, is not pictured on this diagram because we haven't drawn a free body diagram for the Earth. We're only considering the forces acting on the apples, and there's definitely a force of gravity acting on the apples. We just haven't pictured that equal and opposite force on the diagram. And these same arguments we can make for the normal forces on the bobcat, the normal force on the bobcat and the force of gravity on the bobcat too. So I won't add them there. The only extra force here that we haven't considered is F. So F, the push force that I'm supplying. So if I'm pushing the box of apples, then the box of apples must be pushing me too. But because we haven't drawn a free body diagram for me, that paired force isn't represented here on the diagram either. But what would it be? It would be the force that the box of apples pushes on me with. That's, again, not pictured on this diagram. So there's a lot of paired forces here that aren't represented on the diagram. They still exist. They're just not part of our problem right now. All we're concerned with is the motion of this apple box and the bobcat box and how they interact with each other. We're not really concerned with what's happening to me. We could expand the problem to include me, and then we would see that paired force with the force that I'm applying on the apples there, but that's not the problem that we're working on. Okay, those are the force pairs. That was part 2. So now let's try some quantitative problem solving. All right, my organization here isn't great, but I hope that it kind of makes sense and you can bear with me. All right, so for 3, now we've got that force is equal to 20 newtons. The mass of the apple box is 5 kilograms. The mass of the bobcat box is 20 kilograms. And the question is, what's the acceleration of these boxes? So let's use our free body diagrams and Newton's second law here to help us do this. So what we can say for sure is that the net force in the x direction is equal to mass times acceleration in the x direction. And that's true for both boxes. So what I will do is I'll write for box A, the net force on box A in the x direction is equal to the mass of A times the acceleration of A, which is equal to the force that I'm pushing with minus the force of that B pushes on it with. Okay. But then also I can write that the net force in the x direction on box B is MB times AB, which is just equal to FAB. Okay, let me scroll down. So it looks like I have more unknowns than I have equations. It looks like I have acceleration as an unknown, acceleration A, acceleration B is an unknown, and I have this interaction force as an unknown here too. We're given the force that I'm pushing with, so that's a given, and we're given the masses. But, so this is where some physical intuition comes in. If I push on the apple box and it pushes the bobcat box, then those two boxes, as long as they stay in contact, must accelerate at the same rate. So we actually also know this, and I'm just going to call those acceleration. So we know that MA times A equals F minus FBA. And we also know that due to Newton's third law, FAB is equal to FBA. Those magnitudes are the same. So we also know that FB times A, which is equal to FAB, these two things are the same. So I can plug in the second equation here to the first equation. So let me do that. So just taking the second equation and plugging it into the first, the MA for block A is equal to F minus MB times A. And if I solve that, I can rearrange F equals MA plus MB times the acceleration. Okay, so then the acceleration is equal to just the force that I applied over the combined masses of the boxes, excuse me. That kind of makes sense. So let me plug that in. So 20 over 20 plus 5 is 25. So that's 0.8 meters per second squared. Okay, so how do we interpret that? That says that when I push on the apple box, it's really like I'm pushing on a much larger box that has the mass of both the apple box and the bobcat box. That kind of makes sense. So that checks out intuitively, at least for me. The last part of this problem that I want to do is to solve for the force exchange between the two boxes. So that is the magnitude of FAB and FBA. So really what we're doing here is we're trying to find FAB and FBA. That's the last part, finding the exchange force between them. Now that I know the acceleration, that's pretty straightforward, actually, because I have this equation right here, which will let me just calculate FAB directly, now that I know acceleration. So I can take mb times a, which is equal to, mb is 20, the acceleration is 0.8, and that's equal to, can I do this math in my head? 16 newtons. So, all right, let me box some of this stuff. So which is equal to FAB and FBA. So that's how much force is exchanged between the two boxes. The Apple box pushes on the Bobcat box with 16 newtons of force and vice versa. All right, that's the acceleration there. Okay, so if we look back up at our original diagram, the free body diagrams, if you look at, so this force is 20 in this problem, this force is 16. So we lose a lot of acceleration to that second box. That second box pushes back on us really hard. And the bigger that second box gets, the bigger this force gets too. And you can check that in the math if you want to try it with a couple of different masses. But that's how we approach these problems. We break it into free body diagrams, and then we can set up Newton's second law, which is what we did down here, to solve for the quantities that we want. The second part where we thought about the third law of pairs is conceptually pretty important, because we used the fact that the exchange forces were third law pairs here to make our equations work and to give us additional information. So I hope that helped you understand Newton's third law and how you might use it in a problem-solving context. We'll work on more problems like this next time I see you. So I'll talk to you soon. Okay, bye.